Hey everybody. Last week we talked about constant acceleration and graphs of motion, distance time, velocity time graphs when something's accelerating at a constant rate. I had a little um, computer program that plotted a car as it went down a hill of constant slope. And I asked you to make some predictions, and then we looked at some graphs. And one of you in office hours suggested that maybe making a quick video that is clear, precise, and gets at what I was trying to get across would be a good idea. So I'm doing that right now. I'm going to ask you to consider an object that is dropped from rest and accelerates for a few seconds, maybe 6 seconds. And we are going to look at what happens to these quantities as those 6 seconds goes by. Time obviously going to go by. Our rate of acceleration is gravity, so that's constant. What happens to its velocity as a function of this acceleration? What happens to the distance traveled or its displacement from the starting point? So our times are going to be 0 seconds, 1 second, 2 seconds, 3. Now, the acceleration. We've talked about for a long time now it being negative 9.8, negative because it's directed downward, and 9.8 because that's the value of our planet at sea level. I'm going to suggest that we modify that two ways. Number one, let's just round it to 10. Secondly, just so that our graphs are in quadrant 1, let's just use positive 10 as the acceleration. And knowing in our minds it's downward, but we're going to use a positive 10. So let's put down the acceleration at the beginning. Well, at the beginning, it's 10 meters per second squared. And then after 1 second, it's still accelerating on Earth at a constant rate of 10 meters per second squared. Now, some of you might find it interesting that I put 10 for the first one, that is 0 seconds of time gone by. And you might not feel comfortable with that. Think about this for a moment. When I'm holding it, gravity is acting on it, but I'm preventing it from accelerating. The instant that I drop it, it begins to accelerate at this rate. So if I start my timer at the instant I let go, even though it really hasn't moved very fast yet, nor gone very far, it is accelerating at that rate. So our constant rate of acceleration the whole time is our 10 meters per second squared. Now let's look at what happens to its velocity as a result of that constant acceleration. And I said, if I didn't say we're going to calculate it, we're going to calculate it. We're going to use our equations of kinematics. I'm going to suggest that since we know time and acceleration, and we're dropping it, so the initial velocity is 0, I'm going to suggest that the first equation be the one that we use. So we have v equals v naught plus at. This is 0 because the initial velocity of a dropped object is 0. So this just becomes v equals at. So we have 10 meters per second squared is our acceleration, and time. Now, again, it's downward. We know that. And to be true, we would have a negative sign there, but then our graph would be in the fourth quadrant or something like that. And I'd rather just be in the first quadrant when we graph it. So put in our initial time, 0 time. Well, 0 times 10 is 0. So we end up, after no time has gone by, not having a velocity yet. That makes sense to me. I hope it makes sense to you. Let's change the time to 1 second. 1 times 10 is 10 meters per second. So after 1 second, the object is going 10 meters per second at the end of 1 second. At the end of the second, 2 times 10 is 20. Again, these are downward. We would probably put a negative sign if we were just doing problems on paper. But again, for graphing's sake, I'm going to keep this all positive. 3 seconds. At the end of 3 seconds, accelerating the whole time at 10 meters per second squared in the downward direction, we now are going 30, 3 times 10. So we have data that you could probably look at it and see how it's going to graph, but we're going to do that too. To determine the displacement, x, we're going to use one of our equations of kinematics. We could use this one solved there, but we need to plug in those final velocities we just calculated. We could use this one, but again, we calculated some velocity. Let's use this one because look, this is 0, because 0 times any time is 0, and the initial velocity is 0. We have 1/2 a, which we know is 10, and time squared, piece of cake. Let's do it. So we start out with x equals v naught times t plus 1/2 at squared, realizing all the while that this term is 0 for any time. This simplifies to x equals 1/2 at squared. Let's make little parentheses, placeholders, so to speak, to put in our values. Now our a is 10 for every time. Our time is going to get squared. Now our first time is 0. 0 squared is 0. 0 times 10 is 0, and half of 0 is 0. So after no time has gone by yet, it hasn't gone anywhere. That again makes some sense. Let's put in 1 second. At the end of 1 second, how far has it been displaced from the location it was dropped? How far has it traveled below that dropping point? 1 squared is 1. 1 times 10 is 10. Half of that is 5. Interesting. And we haven't talked a lot about that number being 5, but that is how far an object falls on Earth at the end of 1 second. A lot of kids want to say it's 10, but the distance is not 10. The distance is half of that, actually. Now, how do we use 9.8? This would be 4.9, but call it, between friends, call it 5. 2 seconds. At the end of 2 seconds, how far has it fallen? 2 squared is 4. 4 times 10 is 40. Half of that is 20. Interesting. The gap here, the difference here is 5. The difference here is 15. Because you're going faster and faster and faster. Okay. Quickly, let's round out our table. 3 seconds squared is 9. 9 times 10 is 90. Half of 90 is 45. 4 seconds squared is 16. Times 10 is 160. Half of that is 80. 5 squared is 25. Times 10 is 250. Half of that is 125. And the last one, 6 seconds. At the end of 6 seconds, how far has it fallen? 6 squared is 36. Times 10 is 360. Half of that is 180. Okay. These gaps are getting bigger and bigger. The difference here between 45 and 20 is 25. And the difference down here between 180 and 125 is 55. So it's traveling way farther between the 5th and 6th second than it did between the 1st and 2nd second. But again, that's because it's going so much faster at later times. Let's plot that real quick. So I'd like to plot velocity time first. Okay, so let's plot this velocity as a function of time. I'll try to be neat and tidy about this, but let's go quick. 0 seconds, 0 meters per second. 1 second, 10. 2 seconds, 20, etc. 0, 0, 1, 10. Okay, so how does that data look to us? It's the graph of how fast you're traveling as time goes on. And how fast you're traveling seems to be jumping by 10 every second. So if we were to take a ruler, meter stick, whatever, that's linear data, right? There's no question about it. Now I plotted it as carefully as I could in the interest of time, and it's not perfect, but for the most part, that is linear data. Let's look at the distance as a function of time. Our distances are 0 after 0 seconds, 5 meters after 1 second, 20, 45, 80. Let's plot that. 0, 0. 1 second is 5. I scaled this 25, 50, 75, 100, etc. After 2 seconds, we have 20. Well, that's under 25. Let's say that's about right. 3 seconds is 45. That's just shy of 50. Is this data linear data? Like our velocity time data was a line? Well, no, it's not linear. This is clearly some sort of exponential function. I think what we call it in math class is a power function, a square power function. But I'm just trying to smooth that out a little bit. It's not the end of the world that it isn't real perfect, but it's clearly not linear. And that also kind of makes sense, right? We know that when you fall, or an object falls, that it's going faster and faster and faster as time gets longer. And if you're going faster in a given time interval, you're going to cover a greater distance. So that's why there's just no way, I would hope you'd say, if you're accelerating, that it looks like this, because it doesn't. And your velocity looks like that, yes, but your distance is going to be a power function, a square power function. I hope that was helpful. I hope that was clean, and I hope that helps you visualize what the graphs of motion for an accelerating object look like.